Now that you've seen what a simple ConvNet looks like, there are many things that we can do to improve it. We're going to talk about 3 of them: pooling, one-by-one convolutions, and something a bit more advanced called the inception architecture. The first improvement is a better way to reduce the spatial extent of your feature maps in the convolutional pyramid. Until now, we've used striding to shift the filters by a few pixels each time and reduce the feature map size. This is a very aggressive way to downsample an image. It removes a lot of information. What if instead of skipping 1 in every 2 convolutions, we still ran with a very small stride, say for example 1, but then took all the convolutions in a neighborhood and combined them somehow? That operation is called pooling, and there are a few ways to go about it. The most common is max pooling. At every point on the feature map, look at a small neighborhood around that point and compute the maximum of all the responses around it. There are some advantages to using max pooling. First, it doesn't add to your number of parameters, so you don't risk an increase in overfitting. Second, it simply often yields more accurate models. However, since the convolutions that run below run at a lower stride, the model then becomes a lot more expensive to compute. And now you have even more hyperparameters to worry about: the pooling region size and the pooling stride. And no, they don't have to be the same. A very typical architecture for a ConvNet is a few layers alternating convolutions and max pooling, followed by a few fully connected layers at the top. The first famous model to use this architecture was LeNet 5, designed by Yann LeCun to do character recognition back in 1998. Modern convolutional networks such as AlexNet, which famously won the competitive ImageNet Object Recognition Challenge in 2012, used a very similar architecture with a few wrinkles. Another notable form of pooling is average pooling. Instead of taking the max, just take an average over the window of pixels around a specific location. It's a little bit like providing a blurred, low-resolution view of the feature map below. We're going to take advantage of that shortly.